Hello, we are here now to start chapter 7, which is techniques of integration. In chapter 6, we saw some applications of integration, and there are quite a bit of applications left, which we will see later in chapter 7. But before getting into those applications, we want to explore methods which help us find the antiderivatives of a little bit complicated functions or the type of functions which we have not yet learned. You have to remember that integration is generally more difficult than differentiation, and the reason is because there is no set rule or no set method which will always work for certain problems. So for example, in the case of differentiation, when you see a product, you know that product rule is going to work, and then if you see a quotient, finding the derivative, you can use the quotient rule and so on. But now in integration, we don't have things like that. So how do we then find the antiderivatives? Now there are some examples which cannot be anti-differentiated. So for example, this integral e to the x square dx, this can actually not be anti-differentiated. Symbolically means in terms of a function of x. Now we can solve it numerically. In other words, when we have values, when we have the definite integral, then we can, but those are more like numerical methods which we have not learned or you have not learned yet. So, but there are some techniques which work most of the time, and these are the main basic three techniques: algebraic manipulation, substitution, and integration by parts. Now, the first two we have already seen, the algebraic manipulation and the substitution. So for example, the algebraic manipulation, like the one example that I gave you, if you have something like this, then you can do the substitution and do some algebraic manipulation, and you should be able to get the answer. Also, there are other examples you have seen. Substitution also you have seen the example. So now in this section we will learn integration by parts. So how does that work? Now one thing you have to remember, that integration by parts is not a product rule for anti-differentiation. There is no such thing as product rule for anti-differentiation. But in order to find the formula for integration by parts, we do look at a product of functions and we try to differentiate it. So we are looking at this product of two functions and we are taking the derivative, and remember from Calc 1 we apply the product rule and we get this. Now if we anti-differentiate both sides, so I am just putting the the symbol, and the left hand side becomes fx dx because the derivative, you take the derivative and antiderivative of it gives you back your function. The right hand sides I keep them exactly the same and as in the previous step. Now I'm going to rearrange these terms, so kind of leave this term here and move this one on the other side, and we end up getting this formula, which is the formula for integration by parts. Now if you can remember it this way, good. Otherwise there is a easier way to remember the formula for integration by parts, and we say that if we think of u to be f of x and v to be g of x, then du will be f prime of x dx and the dv is equal to g prime of x dx. The differentials will be there, so that the formula up here, the one in the box, can now be written as this formula, which is the one we will be using when we do the integration by parts. So now remember, as this is telling you on the left hand side, when you see two functions in your integrand, you are not going to call one of them as f and the other as g. One of them will be f, the other will be actually g prime. So in terms of u and v, one of them will be u, the other will be taken as dv, and then we will go from there. So now when you see a problem, the first thing is how to figure out which one to pick as v and which one to pick as u and which one to pick as dv. Well, the idea here is that you should pick dv to be the function which can easily be integrated, or whose integral you know already or can be easily found. And also not only that, but you have to look a little bit ahead. Remember, we are getting in our formula this another integral coming up in the formula, right? This one. So once you applied this step, this integral must be simpler than the given integral. If it is complicated, you have to go back and redo your substitutions. So let us look at this. So we have two functions here. One is x, one is e to the x. So which one is easily integrable? Well, actually both of them are, aren't they? So because this is going to give you x squared over 2, and when you anti-differentiate the second one, you are going to get e to the x. So both are easily anti-differentiable. So what if we take u to be e to the x and dv? So how will you pick the dv? Remember, it will be the other function multiplied by dx. So then once you pick these, the next step will be for you to find du, and in this case you will be finding v's, which means you will be anti-differentiating it. Well, du will be equal to, in this case, e to the x dx, and v in this case will be x squared over 2. Now we don't put the plus c here, and the reason is because remember, x squared plus 2 is one of the antiderivatives, and so we are just looking at the simplest antiderivative just to keep our calculation simple. So that now the formula is u dv is equal to u times v minus integral v du. Now we plug in. So we have actually let's write it like this: e to the x times x dx, because remember this is our u and this is our dv. So is equal to uv. U is e to the x, v is x squared over 2. So e to the x times x squared over 2 minus integral v, which is x squared over 2, times du, which is e to the x dx. But look now here, what happened? This expression which we got for that one, it is complicated. Then the given was this. So this one became more complicated, which means that the choice that we took for u and v is not good. So it means we have to go back and kind of cross this, and we have to redo our problem by choosing u to be x and dv to be e to the x dx. Okay, so if we do this, then our du is going to be dx and v is going to be just e to the x. So now integral, remember I'll write the formula here, u dv equals uv minus integral v du. I encourage you to write this formula every time you use integration by parts so that you remember it. So now we have our given expression is x e to the x dx. So this is now equal to uv. So what is u? In our case, x. So x times v, which is e to the x, minus integral v, which is e to the x, times du. But du is just dx. So that this integral is very, very easy to solve. So we end up getting x e to the x minus e to the x. And now we will put a plus c here. So this is our answer. And someone might say, well, I'm not sure, well, is this correct really? So what you can do is you can check. And how can you check? If you differentiate this expression, what do you end up getting? Well, on the first term, you will have to apply the product rule. So keep x as it is, take the derivative of e to the x, which is e to the x, plus keep e to the x as it is, take the derivative of x, which is 1. So I get 1 into e to the x, minus the derivative of e to the x, which is just e to the x, plus derivative of c, which is 0. And now this cancels out and you end up getting x e to the x. So which is what we have here, and that's what we wanted. So this is how we apply the integration by parts. Now I'm going to show you a slick trick actually, which works most of the time but not always. And this is called a Layette method. No, not every instructor introduces this, because this method doesn't work for like every time. But I think it's a good idea to know it, because it saves you a lot of time when you have to pick your u and dv. So the method states, or according to this method, we have to pick u to be the function that comes first in the following list. And this method works often when the functions inside the integral are two different kinds of functions. And we are talking about these 5 types of functions. So the first one, L, represents logarithmic, I is for inverse trig, A is for algebraic, T for trig functions, and E is for exponential functions. So if you go back to our previous problem, remember we had in x times e to the x. That is what we were going to anti-differentiate. So we have a function x and then we have ex. So this is an algebraic function and this is an exponential function. So if you go to the list, can you see A is coming first? So A is the one that we should pick as u, and then the other one will automatically become dv. So now looking at this example, we have x squared times sine x. So sine x is an trig function and x squared is algebraic function. So in the list, A is coming first. So we will start by saying let u equals x squared and dv equals sine x. And remember, dx will come along with it. You will not take dv to be just sine x, it is sine x dx. So these are the steps you have to remember. The first thing is to pick your u and dv. The next step is to find du and find v. So you differentiate this function, the u, and you anti-differentiate this other one. So the antiderivative of sine is, remember, the negative cosine. So writing the formula, that integral of u dv equals uv minus integral v du. So that x squared times sine of x dx equals, now remember here, this is very, very important that you remember that the what is u and what is v. So just to remind you, this is your u and this is your dv. Okay, so this is now u times v. So u is x squared and v is minus cosine x minus integral of v, which is minus cosine x, times du, which is 2x dx. So that we end up getting is equal to minus x squared cosine x plus 2 times x cosine x. dx. Okay, so are we done? No. Why? Because we still see an antiderivative, so we shouldn't have this sign on the left when we are done. So we should have integrated every expression. So it means now we need to work on this quantity. So how will you do that? It looks like we have to apply integration by parts again. So we have to apply integration by parts on the x cosine x dx. So what I recommend is we pick x cosine x dx, and I'm going to write it over here and work with this. So now for this one, again I'll say let u equals, then going back to our trick, we will take u to be x and dv to be cosine of x dx. So that du is dx and v is going to be sine x. So coming back, remember u dv equals uv minus integral v du. So coming back here, this will become u times v. U is x, so x times sine x minus integral of v, which is sine x, times u du, which is dx, which is going to give me x sine x plus cosine x. And now we just go back, plug this back in there, and we end up getting our answer. So we will go back. Therefore, the quantity which we actually had to anti-differentiate is equal to minus x squared cosine x plus, now remember there is this 2 which will be distributed over the quantity, so we end up getting 2 times x sine x plus 2 cosine x, and then now here we can put a c. So this is how we do our integration by parts. In the next video we will look at a little bit more complicated examples.